All right, welcome to Computer Science 4423 5523 Software Evolution. And today we're going to be talking about evolution and maintenance models. So this whole week is all about these things, and so we'll be talking a bit about them as we go. Um, so hopefully the outcomes of today's lecture is that you'll know about the general idea of a model for software maintenance and evolution. Be aware of what we call the reuse-oriented model. Be aware of the stage models for CSS, so closed source software, and of course, stage model for FLOSS, the free libre open source systems, and also be aware of the change mean cycle model. So these things are very akin to what we might call they're similar to like when you took 3307, 3321, or something similar to that, your introduction to software engineering course that kind of talked about the software development lifecycle. You know, it's a little stick and box diagram that is supposed to be this generalized picture of kind of how these models actually, like how we actually do things and the process by which we can conduct either software development in the case of the SDLC or software maintenance in the case of the SMLC. All right. So the general idea, right? I just mentioned this was that we have the traditional software development lifecycle, and we show below, okay, and which describes the two basic phases, right? We have development, and we have maintenance. And so in our development phase, right, we have requirements definition, preliminary design, detailed design, implementation, testing. And then once we get our first release done, then we hit this operations and maintenance period, which is just where we sit, okay? We go through this whole thing, iterate, and then we eventually get to this place where we're just doing maintenance, right? The interesting thing is if you look below, the percentages are telling us our relative costs. So we have 3% for requirements, relative cost in time or effort percentage. Preliminary design, detailed design is 5%, is implementation 7%, testing 15%, operation and maintenance 67%. So 2/3 of our product lifespan cost is found in the operation and maintenance component. So it might be wise for us to think that there may be a need for some sort of a way to manage this. And so we have to understand that, of course, software maintenance is going to have some unique characteristics, right? And these things include the constraints of the existing system. So we have an actual system. It's operational. So anything that we do to it must be consistent within the constraints of that original design or architecture and has to work with the original code, right? We can't be just all of a sudden changing everything, right? There was a set of requirements by which that constrain the original system that we have to maintain. We tend to have a short time frame when we're actually doing this, right? A maintenance activity tends to take maybe only a few hours to a few months, whereas, actual development, the original implementation, can span, for 1 or more years. So we're doing very small changes to this and getting them out there to get them going. Available test data. And so in software development, right, test cases are designed from scratch, whereas in maintenance, we can actually select from test cases and execute them as regression tests. So we have the beauty of having already existing tests that we can work with, that we can actually verify our changes are working correctly. So then, because of these three primary characteristics that are unique to software maintenance, many have proposed that we need to have our own software maintenance lifecycle, right? So, because we have to deal with these unique activities. So that brought us to a couple of ideas, right? The idea of course, maintenance is that we obtain a new version from an old system by modifying one or several components, okay, or even adding in new components. And because of that, 3 process models were proposed by Vic Basili. Vic Basili is well known to be one of the probably one of the greatest software engineering researchers to ever lived. I think he is still alive. I met him a couple years ago. He's a really interesting dude. and he talks about these three models, right? The quick fix model, where we essentially make really quick changes to the code and then to the accompanying documentation, and then get them into the system and release the system again. We have the iterative enhancement model, where we first changes are made to the highest level documents, and then eventually changes are propagated down to the code level. And then finally, we have the full reuse model, where a new system is built from components of the old system and others available in the repository. Okay, so what we do in the quick fix model, which I'll show you in a second here, we have three steps, right? We first modify the source code to fix the problem. Then any of the changes that we made, we have to update the relevant documentation, and then we recompile the project and produce a new version. Okay. Changes the source code made with no prior investigation, such as analysis, impact change, ripple effects, or regression testing. We just break out the fix and get it going. And so it kind of looks like this, right? We requirements, design, and tests kind of remain the same, but we change the code, and then that code change will then impact our design, requirements, and tests, right? So our documentation up top and our tests, we have to make sure those work, and then we're done, right? Old system to a new system. Pretty simple. We just fix the code in the old system to create the new system, update the documentation, release. Sounds simple, although it should only probably be used for really easy to do fixes, because the more quick fixes you make, you're going to end up causing more problems in the code, and going towards, and these changes will cause decay. Decay will then lead to having to replace the system faster. Reuse-oriented models continued. So we have, before we get into the next one, the incremental one, we have to understand the difference between iterative and incremental in the world of software engineering. All right. They're often used a little liberally, right, as if they're interchangeable. So this iteration and increment concept. Unfortunately, they are not. In software engineering, they have two specific meanings, right? Iteration really just means that a process is basically cyclical, and meaning that the activities and processes are repeatedly executed in a structured manner. Iterative development is based on scheduling strategies in which time is set aside to improve and revise parts of the system under development, right? We should all know about this. We've all seen the iterative development life cycles. Incremental development is a combination of both staging and scheduling strategies in which parts of the system are developed at different times and or paces and integrate as they complete. So you have this, you build a little bit up, and then, so you have multiple phases going on, and then of different components and different sections of the system, and then you start integrating them near the end to create a release. Iterative means that we are simply working a cycle, right? It's just based on scheduling strategy, which we set aside different time to improve and revise parts of the system under development. So you have to understand the kind of the difference between these two ideas. All right, and we're going to look at that in a second here. But the iterative enhancement model, which we'll show in the next figure, depicts how the changes will flow from the top level of documents to the lowest level documents or code. And so we start, as I already mentioned, we start with existing system artifacts. So we have requirements, design, code, test, analysis documents. Okay. And we're going to start by revising those high-level ones that are going to be affected by the changes and propagate that change down through the low-level documents. This allows us to essentially redesign the system based on an analysis of the existing system. Okay, so you can think of it like this. We start here at requirements, right? We analyze what's going on with that, and then we weave ourselves all the way down through design, code, test, and into analysis. And we use that. Once we have this kind of figured out, we make a change through these documents, and then we analyze that, and then we go and make a change down through and propagate that to each of those levels of the system. Okay. And then we continue this, right? It continues. It's a process that we follow. Um, Useful. This is probably a more useful way of doing things. Now, the next one that we're going to talk about is probably the most, well, I don't know if it's the next one necessarily, but soon. There's a much more useful way of doing this that actually gets into the depth of how we actually would pull this off. So the main assumption, the final one is the full reuse model. And this is based on you have a repository of existing code ready to go. Okay, so more like what we would normally see in a regular development, where we have like a Git repo or something similar to that, Subversion, Mercurial, whatever it might be, or a more commercial grade one like ClearCase or something like that. We have this we have the available artifacts, okay, of earlier versions of the system. And what we want to do is we want to focus on reuse, right? We're very explicit in our use of reuse, and we have 4 primary activities that we're going to do, right? We're going to go and look through the old system, identify components that exist there, and see which are potential candidates for reuse. We're going to understand that we're going to work through to try to understand the identified components, and then we're going to modify those old system components to support whatever new requirements that we have. And we're going to integrate the modified components to form the newly developed system. So it looks something like this, right? We're going to go through the old system. We're looking inside the repository. Okay. So our old system, our requirements, design, code, test, all go into the repository as different components of that repository. So the requirements, design, code, test artifacts, right? And then what we're going to do to build our new system is we're going to pull existing artifacts, right, from it, and the I here represents the ith iteration of the system. So they're not necessarily all from the same component of the same part of the same version of the system. They can be from different versions. We'll pull all these things in that are our candidates, and we essentially construct this new version of the system from these existing components, as much reuse as we possibly can get. So just bear that in mind. All right, so these are kind of like really high level views of how we might do this. Now, from that, okay, Rajlich and Bennett present a descriptive model of software evolution, which they call the staged model of maintenance and evolution. Okay, and we're going to look at that in a second here. And its primary objective is at improving understanding of how long-lived software evolves, rather than aiding in its management. And so their model divides lifespan into 4 stages. It's actually 5, but the 5th one is not a stage. It's more just what happens. And so the first thing they talk about, and bear in mind, this is not how we manage things. The prior one, the prior 3 from Basili, are all about management, right? How do we actually do this? This is more understanding what happens when we're actually building, okay? So during initial development, the first delivered version is produced. Knowledge about the system is fresh and constantly changing. In fact, change is the rule rather than the exception, right? We've all talked about that in the original in software engineering. And so, but eventually some sort of an architecture will emerge and stabilize. Then we hit evolution. Evolution is where simple changes are easily performed. More major changes are possible too, but the cost and risk is greater than in the previous stage. So evolution, the cost and risk to, if you break the system, is higher than when you were in initial development. We should still have good knowledge of the system, although the original developers may have moved on. And then for many systems, most of the lifespan is spent in this place, right? And for the most part, and the reason why you should be even taking this course is that more than likely when you go out there in the field, this is what you're going to be doing. You're going to be in this evolution phase where you're evolving the system. You're most likely not going to be initially starting out on initial development unless you go work for a newer company or a startup or something similar to that. And then from there, right, they add in servicing. Servicing is the next phase after evolution, right? Where the system is no longer a key asset for the developers. They are mostly focused on maintenance tasks rather than architectural functional changes. Knowledge about the system is lessened, and the effects of the change become harder to predict. Cost and risk of change have increased significantly. And then finally, we hit phase out. And phase out, where we are at this point where we made a decision, right? Where we're going to replace or eliminate the system entirely. Okay, and we're just trying to figure out how we're going to deal with this. And the reason we made that decision was just the cost of maintaining the old system is prohibitive. It's and we're already in the middle of working on or we're already in the middle of working on a new system to replace the old one, and we're just waiting to get it finished. And thus we've created an exit strategy. And oftentimes we utilize techniques like wrapping and data migration, which we will talk about when we get to legacy systems. And then ultimately the system will be shut down. And so if we look at this, right, this is kind of this model, right? So we have our initial development, produce that, as we just said, our first running version. Then we hit evolution, right? We still have that good knowledge, right? We got that initial thing out. We have that good knowledge still. And we just keep adding these evolutionary changes, right? So it's an iterative approach. We iterate on this evolution until a point where we can no longer evolve. So we are really not adding anything new. And then we just become servicing. And so we start servicing this this product, right? We add in new patches as we go, right? We find bugs, we fix them. And then eventually we stop. We stop dealing with that and we get to this phase out. So we figured out either we're going to find a solution to replace this, or we're building one, or but we've made the decision to get rid of this thing. It's just waiting to go. And then finally, once we get that solution in place, we can switch that system off, and we go into close down, and the system's gone. Okay, so that's the general staged model for closed source systems. Additionally, we can have a much more what we might call an incremental stage system, where it's staged not only in the ideal, right, where we have initial development, evolution, staging, etc., and then eventually phase it out. But we are actually looking at each version and doing this process, possibly even simultaneously. So we have first running version, right? We create evolution, and then we hit V1 for evolution, right? So version 1 evolution has the evolutionary changes servicing for V1, servicing patches, phase out V1, close down. As we get to close down, that's when we start really evolving version 2, right? So we made a major evolution, possibly during the phase out phase here for V1. We've started creating this version 2, and we're evolving that, right? And you can think of this as, like, for example, think of like the Windows operating system, right? And those have a certain lifespan, or even like Ubuntu. Ubuntu every 2 years has a long-term service version that comes out, and that's good for 2-3 years. But eventually they stop servicing it, and they phase it out, right? Windows does the same thing, or at least they used to. Now they're kind of just operating on Windows 10 for the rest of eternity. But so we evolve this, and we service it, and we phase it out, and we just keep doing this over and over. This is more like what you will probably see when you're out in the field. Something similar to this kind of evolution, where we have multiple versions of the product. We want to eventually get rid of it, right? Because people are going to continue using. This is especially important for general purpose software that kind of goes to the masses, is that there's going to be people who are going to be using the oldest version that you support out there, and possibly even ones that you no longer support. Like, was it Windows, like Windows 8 had finally come out. I think people are still using 95 out there. I mean, a system from almost 2 decades ago, people were still using. So, this happens. So just bear that in mind. And there hadn't been patches or anything for that forever. So people will continue using these things for the rest of eternity, and even after you've hit close down. But you eventually have to say, look, we're not going to support this anymore, and you're on your own. So Additionally, they came up with there was a notion for FLOSS, right? A stage model for free, liberal, open source um, systems. And so, well, it hasn't actually been visually highlighted, but the three major system differences are identified between CSS and FLOSS systems, right? The figure, initial development here is it's not actually visually highlighted, but it can be it's the only initial development stage in the evolution of a FLOSS system. There's only one. And so when this was actually developed based off of some empirical work looking at these FLOSS systems, right? And so what they noticed was that when some systems were analyzed after a transition from evolution to servicing, so they moved to servicing, right? A new period of evolution was observed. Okay, so it somehow managed to go back to evolution. And that's what this broken line was, right? And you can actually go from phase out back to evolution as well. And what ends up happening is that you get new developers, right? So oftentimes there are like projects. For example, there was this book by Eric S. Raymond. Well, it wasn't a book originally; it was an article that he wrote that became a book called "The Cathedral and the Bazaar." And in the first half of it, really the book is about understanding open source development versus closed source development. But he'd been an open source developer forever. He actually picked up and shifted the SendMail project from phase out all the way back to evolution. And because of that work he was doing, he actually showed that this is actually possible. But the key thing that he was actually looking at in that article was, not only the difference between open source and closed source, but the difference between vast majority of open source projects and Linux, and what happened with that. And that was a pretty interesting read. Okay, so all these things that we've seen before, right? The stage models, these things are all about kind of observations of what happens in these types of systems. But the more interesting one is what happens, is this thing, right? This change mini cycle. Okay, this is more interesting for how it's actually done. Okay, and this was proposed by Ya et al. Back in the late 70s. This is like an old idea that actually got renewed because we started seeing that it might actually work. So software change is a process that may introduce new requirements to the existing system, may alter the software system if requirements are not correctly implemented, right? Obviously, we have bugs or we misunderstood what the user wanted or whatever, and we need to fix the system, okay? And so this change mini cycle idea is basically we get a change request, right? That change request, we then go in to the system, we analyze it, and we plan the change, right? This requires us to do program comprehension and change impact analysis, okay? If after this we realize that the request is no good, we will reject the request, and then we go and find the next change request that we're going to look at. We do the same process. If we eventually get through and we accept that we're going to work on this change request, we then go to implement the change. So we have to do restructuring, or what we'll call refactoring in OO systems. And then we propagate the change, okay? So we work it through and propagate the change not only through the rest of the code, but also through the documentation. We verify and validate, so we run our tests. If we don't pass through this, we go back and we have to keep changing it until we do. Once we get through verify and validate, we update the documentation, and we go select our next change request. It's a pretty simple idea, right? But this is the basis for basically all the tools that we have out there to help us with this. So bug tracking tools, a lot of the stuff with how we operate like a Git, so source code management and things like that, or software configuration management. All these different things are all based on essentially the ideas that kind of came from this mini cycle model. All right. Okay, so that's kind of the end of today's lecture. If you have any questions, well, before we get there, so go back through, review chapter 3.1 through 3.5, which is what this talks about, everything we just talked about. And then go ahead and read chapter 3.6 through 3.7. Watch lecture 5. And then if you're in 4423, work on homework 1, right? It's been assigned starting Monday. And then look into 4423. Make sure you get... So there's a course project, right? For 4423 course project, the first part is due this coming Friday. So what was that? The looks like the 22nd at 11 p.m. So you have to get that done. You have to form teams. I would suggest using Discord and contacting your just send out a message and see if you can get some people to PM you. You have to have this thing set up, and I need to know who your teams are by basically Friday at 11 p.m. All right, make it happen. Okay. If you have any questions, you can always contact me through. You can send me a message through Discord. I do check it periodically. Send me an email. I check that all the time. Stop by my office hours Tuesday, Thursdays, or any other way of getting a hold of me. You guys have a great day. I'll talk to y'all later. Enjoy.